Ben Pearce. Welcome to the podcast again.
Thanks, Julie. Glad to be here again.
Yeah, it's really exciting. You're the first guest that's a return guest, actually. So it's kind of a
Oh,
huge
cool.
pleasure at my end. For people who haven't heard your initial recording with me, you are a PhD student at McMaster University in astrophysics and astrobiology. So, how are things going with that PhD?
Pretty good. Just finishing up now. Got about maybe 5 more months, and then I will defend over Zoom, I'm sure, and then I'll move on to being a postdoc. So very exciting times.
We were talking before we started recording about your postdoc because I was catching up on news in your life, and you're not exactly allowed to share the explicit details of that postdoc. But do you want to tell us where you'll be moving to essentially?
Yeah, I'm very excited that I've accepted a position at Johns Hopkins University in Baltimore. So I'll be moving south.
That's pretty big news. That's
Yeah.
pretty big. Um, so again, for people who haven't heard the first recording that we did, you study essentially how life came to be on Earth. Do you want to just give a brief resume, just so that because the way I say it is probably not 100% accurate. So
Sure.
why
Yeah.
don't you tell us what you study?
Yeah, so my research is on the origin of biomolecules. Kind of the questions that I'm trying to answer are, where did life get its building blocks? Because the postulate is that if you have the right ingredients settled in the right environment, that life will emerge just through natural processes like chemistry mixed with some geochemistry and physics. So my research is wondering, how did the building blocks get there, and what were those building blocks? And I've looked at meteorites as sources in the past, because a certain class of meteorite has a wide inventory of different biomolecules, like the building blocks of proteins, amino acids, the building blocks of DNA and RNA, and the building blocks of cell walls, and and sugars. They have everything. They're pretty interesting objects. Um, and then lately, for my PhD, I've been kind of working on a little bit of a different hypothesis and focusing on the atmosphere of the early Earth and trying to figure out what could the atmosphere have made, what kind of biomolecules or precursors to those biomolecules could have made so that they can rain down directly into ponds, which are kind of these pristine environments for life to emerge, and then processes in those ponds carry forward to produce first life. So that's kind of the overview.
Yeah, and that's very helpful. I did ask you a whole bunch of questions about the origins of life the last time we spoke, so I'm going to try to not be repetitive this time around. But one thing that just popped into my mind when you were talking just now about meteorites
Mhm.
is that I'm wondering if the meteorites have all these building blocks for life. Where do the building blocks come from? Like, how did they get on the meteorites? That's the thing that I don't understand.
Yeah, this is some of the first research I did. Actually, was trying to figure out how those building blocks got there. So we ran models of the interiors of the parent bodies of these meteorites, which are essentially asteroids. Some could be comets, but just essentially big rocks in space that are 100 kilometers in diameter, like really big things. Um, these things are large enough that their pressures in their interiors and temperatures are high enough to have kind of liquid water, kind of running through. You can imagine streams of liquid water running through these big rocks in space, and because they're isolated from the external environment, they're kind of these amazing places to make biomolecules. Um, not much that can destroy them in there. There's like no UV light can get through all that rock, so they're protected from UV. They're protected from galactic cosmic rays. They're protected from the solar wind. So they're kind of this like nice little reaction environments to make all this cool all this cool organic chemistry. And it really just happens through thermodynamics. Like it's favorable to make biomolecules in these at these temperatures and pressures, um, with these starting molecules. So the kind of starting molecules inside these things are things like they're very small, like hydrogen cyanide, ammonia, methane, water, like just very simple like molecules with maybe two, three, four atoms, um, and those are gathered right from the what's called the protoplanetary disk, or the disk of dust and gas that's originally around the proto sun as the solar system's forming. So you kind of build up your big rocks, and you have these simple components in the inside, and then with this water environment, you kind of can get organic chemistry to start taking place.
Okay, so I'm going to ask the question that non-scientists are probably wondering, which is how do scientists like yourself know what's inside a big rock if it's out in outer space?
Yeah, that's good. That's a good question. There are different types of evidence that we can kind of follow to figure this out. Observations are paramount to the field of astrophysics. So looking at with telescopes at different forming star systems that have these protoplanetary disks. For example, ALMA, which is a radio telescope interferometer in Chile, can take a look at one of these disks and tell you, based on the types of light that are shining back, what kind of molecules are in that disk. So we can kind of formulate that picture. So that's the direct evidence, and it as it turns out, a lot of these disks have the similar compositions. These simple molecules like water and ammonia and methane, they seem to be pretty universal because they're like a low energy molecule. Um, if you're an element, just based on the amount of elements that are in the universe, you're most likely to make these things just because they are the simplest, lowest energy species out there. So there's also the theoretical side. It's like we don't expect to see really weird species showing up in these disks that maybe have 12 or 13 atoms attached to them in high abundances, just because it's not the thermodynamics shows it's not really favorable to make something that big um, in these disks. But if you try and make water, the theory will tell you, okay, well, it's really easy to attach two hydrogens to an oxygen atom. Um,
Okay,
so
so
yeah,
you're going based on observation, but also what is like kind of like the rules of physics, so to speak.
yeah, that's kind of the name of the game in my field. Is you use observations and experiments, and then you use present theory that and you try and figure out how this stuff's happening and why it's happening using both kind of components, the observation experiments and the theory.
So outside of the meteorites that fall to Earth all the time, what have we ever drilled into an asteroid? Like, is that something that we've ever done?
Drilled into
Okay, maybe not drilled. That maybe
well,
on in the
well,
movies, but
that's not too far from the truth, though. I mean, that would be the goal, and um, I would say I would be lucky to say yes, but the only probe that had a drill component attached to it was the Philae lander from the Rosetta mission that landed on Comet 67P, but it wasn't able to get its harpoon to work, so it wasn't able to drill, unfortunately, even though it brought one. So we could have potentially found a lot of cool stuff, because it's really under the surface where all the pristine biomolecules are going to be. Because UV radiation, cosmic rays can kind of penetrate to certain depths. Maybe a few centimeters for UV and maybe a meter for cosmic rays. So you want to be able to get as low as you can. But but uh, scientists have been clever, and the Japanese Space Agency just sent, and NASA sent each their own probe to a different asteroid, and they found a way to collect samples in more clever ways. And I think the Japanese team was probably the most clever in that they went down, they took a sample from the surface, and then they sent a projectile. Kind of they sent off an explosion and had a projectile go down and kind of create this crater, exposing the subsurface, and then they took a sample of that region. So it's kind of like maybe the fast way of getting to the subsurface without a drill is just to explode it.
See, I didn't even I guess you don't really know about this news unless you're in the field, right? Because this hasn't gotten all the popularity that the Mars mission has had, for example, right? I mean, I didn't even know. I'm glad I asked the question. Did
Yeah,
they already analyze this sample or is it on its way back to Earth?
it's on its way back, and it's arriving. I think I think one of them's arriving this year, one's arriving next year. So they'll be, yeah. They already know how much. One of them, they already know how much sample they have because they had a camera inside and they could see all these big rock chunks. I think that's the Osiris Rex mission. So both are very
Wow.
exciting. Yeah,
That's super cool. So you must be stoked to read all about the results of this.
yeah. Those results are going to be directly connected to some of the theoretical work that we've done because we have studied we've studied meteorites, and then we did these simulations to figure out the different distributions of biomolecules. So if they measure the biomolecules in these samples, um, and they kind of get our distributions, then that really bolsters our theory, and that's always exciting when you have an experiment or observation which kind of proves the theory.
Could it also disprove?
Yeah, and that would be
Okay.
absolutely fine too, because that means that there's something to be learned, which actually is almost in many ways the better outcome. You want like you don't always want to just get it all right first try because there's nothing really to learn from that process other than this is all true.
Yeah,
It's
it
when
wouldn't be as exciting.
yeah
I would assume if this actually disproved some of the theories that you've come up with, is that that would actually be exciting. I think.
yeah exactly. It's pointing to
Right.
some sort of interesting chemistry or physics or biology that you just didn't expect, and then you got to try and answer why it's there.
Wow. So, are you able to get any information from the meteorites that land on Earth?
Oh yeah, yeah, for sure. Um, a specific class of meteorites, because there's most meteorites that land on Earth are not they don't have biomolecules in them. They're of a certain type that they might be iron based, which you can imagine as the cores of these big asteroids. Um, or they might just be kind of just rock with no not a whole lot of carbon content with them. But maybe about 5% of the meteorites that fall are what's called carbon rich meteorites, and these are the ones that really could have delivered all the cool biomolecules. So different labs will get samples of these, and they will analyze them for one specific type of biomolecule. It's hard to take a single sample and analyze it for everything because you have to take that sample and you have to try and extract as much biomolecule weight as you can. So you have to maybe use hydrochloric acid or some sort of thing to release the biomolecules from the rock matrix, and different types of processes work better for different types of biomolecules. So they'll go through and they'll try and look for some certain type of biomolecule, maybe the building blocks of RNA, which is one of the more exciting ones that I've looked into, and then they'll record the results, and publish them.
That's really cool. Still on the line of the origins of life here, I saw a news post or news article from NASA. The title was "New Insights into How Earth Got Its Nitrogen." Have you read that new article?
New insights in how Earth got its nitrogen. Uh, no, I no, I don't think so. Nothing's kind of triggering in my mind. Um,
Okay, yeah, I was just curious because I saw the headline and I was like, "Oh, I'm not even going to read this. I'm just going to ask Ben about it." Because one of the things, no, no, seriously, because one of the things I'm wondering is when you're in a field like astrophysics and astrobiology, biology, how do you keep on top of all of this new information that comes up, right? I mean,
yeah,
I see this headline, I'm like, "New insights." I'm like, "Okay, like who informs all the other scientists about
Yeah,
this
yeah.
stuff, you know?
Yeah, this is one that I definitely will want to read after this because it's very relevant to my researches. Looking to the earlier Earth's atmosphere and how it got. I mean, it's nitrogen maybe is not as interesting as things like water or methane, um, but it's still because it's an inert gas. It's kind of a source of different nitrogen containing biomolecules, which is key.
What does nitrogen like, what role does it play in the building blocks of life?
The main uh, the main nitrogen species that's interesting for the origin of life is hydrogen cyanide, which is HCN, one hydrogen, one carbon, one nitrogen, and it's kind of the precursor to almost everything um, related to how cells function. Uh,
Oh.
it will react. It will react with different things to make the building blocks of proteins, the building blocks of DNA and RNA, and that includes the sugars and the nucleobases and all this stuff. Um, so so it's getting that hydrogen cyanide, and in order to do that, you need to take a nitrogen molecule, which is two nitrogen atoms attached, and it's a very strong uh, bond because it's a triple bond, and it would rather be in this molecular form rather than single atoms. So you need to be able to split it apart before you can get a nitrogen to make hydrogen cyanide, and to do that, you need usually ultraviolet light from the sun, so it needs to be high in the atmosphere, or lightning, which means you need to be in the troposphere in the lower parts. So that's pretty much how it works. Is you have all this inert N2 sitting around, and then you split it apart and then make cool biomolecules from it.
And you need light to do that.
Yeah, either light or lightning, I
Oh,
guess.
lightning.
Yeah,
That's so
which
true.
which is an which is like the process of lightning actually splitting apart these things is usually a thermal process. So it's the lightning bolt is actually luminescing because it's about 30,000 degrees Kelvin. So it's really really hot, and if you're that hot, you can split apart molecules pretty easily. Um, so that's kind of
Wow.
yeah, it's kind of not really intuitive what's actually happening there when you're looking at it. You see that light flash. You're like, why? What is that? Well, that's just a really hot uh, bit of gas in the atmosphere.
That's so cool.
Yeah.
So cool. I want to move on to Mars only because it's in the news right now. It's hot. We talked a little bit about Mars the last time. I want to get your take on it because I know it's really big that they've sent Perseverance back
Hmm.
to Mars. It's going to collect soil samples.
Yeah.
This is going to be the first time, right?
Yeah. Yeah. Definitely. Yeah. A lot of
So,
exciting stuff.
what do you
Um,
hope that they might uncover?
I think that there's so much cool about that rover. So many cool things related to my research and not related that I still find interesting from kind of like a potential future human settlement standpoint. But because I'm also a big space exploration geek, and I like the idea of potentially like living on Mars someday. Um, which as crazy as it sounds, I don't know. People can dream.
Of course.
But in terms of the science, starting with the science, there's a instrument called Sherlock on Perseverance, which is a what's called a Raman spectrometer, and you essentially has a laser, ultraviolet laser that it shoots at different samples, and then gets those samples to the molecules in that sample to fluoresce, and based on whatever it sees um, in collecting that fluorescence, there's some sort of fingerprint essentially in there, which will tell you what kind of different molecules are present. So what it could find, and based on where the landing site is a really high chance is different of these different biomolecules uh, that are the building blocks of life essentially, and they could be essentially either from life. So there could be living microbes on Mars, and they could just be um, taking a look at the actual organisms, or they could be extinct life. So it could just be the vestiges of past life. You wouldn't really be able to tell with this instrument, unfortunately. whether it was living today or extinct. But both are interesting. So
Could they potentially find things like diatom fossils?
yeah, actually, there's 23 cameras on board Perseverance, and the highest resolution camera is 20 megapixels, which is, I think on Curiosity the highest resolution camera is about 2 megapixels, and if you look at your camera, if you have a new camera, that's probably somewhere like 12 megapixels. So this is a pretty high resolution camera, and it's also got microscope cameras as well. So the highest chance of finding a diatom fossil would be in this sample collection process, where it's going to be digging cores, and then the microscope cameras attached to the end of that mast that took the core. So it'll be able to look, high resolution, zoomed in, to try and see is there any kind of fossil evidence of fossils there. So that's possible. It's that
Yeah,
would
I got
be
shivers
yeah
just thinking about it.
that would be a pretty advanced form of life to find, but would be like obviously like huge if something of that magnitude happened.
Yeah, because isn't this site a site that they think there used to be a lake there?
Yeah, yeah, exactly. Yeah, the Jezero crater filled with water. So high chance of, if life formed on Mars, that there would be some sort of clues here in this location.
Yeah. What are your perhaps personal thoughts on that? Do you think that there was potentially life on Mars?
I I think that I think that there's a probably 100% chance that life, Earth life, um, from some asteroid collision on Earth kind of got transported to Mars. Uh, so I think that there's definitely, and actually with even with the rovers, which is kind of funny, um, it's impossible to sterilize these things to the nth degree. So I feel like we've definitely brought life. Um, but that's kind of like that's an
Yeah, we
aside.
we talked about that last time where when we were talking about tardigrades on Mars and we were
Right.
like, "Oh, well, the chances are pretty high that we'll end up introducing tardigrades on
Yeah.
Mars."
Yeah.
But yeah, it's very, very interesting. I watched it live. First of all, the fact that we could even watch this thing happening. I know it wasn't like actually live. I know there's like a
Yeah.
11-minute delay or something.
Yeah.
But the fact that we could see and we can still see images being broadcasted from Mars is I mean, it is my I can't believe I'm living in this era.
Yeah, yeah, I'm so glad they did that, because it's so hard to visualize. I mean, for me especially, actually, I have sometimes difficulty visualizing things on my own. Like I need that kind of visual aspect in order to help me like figure out what's going on. So seeing the sky crane, seeing the parachute, seeing this thing kind of being dropped down on the surface, it was like remarkable. Like it makes you really wonder, like this. Like you start to think to yourself, like, this was the plan. This seems crazy. Like how was this the plan that they finished on? Because so much had to go right, and it all seemed to work perfectly.
And the testing, I was watching videos of how they tested Ingenuity, the little helicopter
Hmm.
that's on Mars as well, because it's the first time that we fly something like a helicopter on a planet. And I was watching the testing, the QA they were doing on that helicopter to make sure that they could actually work.
Yeah,
I haven't stayed on top of the news. I don't know if they were able to launch it or not.
yeah. I'm not sure about Ingenuity yet. I haven't seen it, photos from it
Yeah.
yet. Yeah,
Yeah, it's pretty cool anyway. So I definitely wanted to bring it up. And especially for you, in your case, I think whatever they discover in the soil samples is going to be very pertinent to your research, I imagine.
yeah, for sure. Um, yeah, I'm going to be looking for the building blocks of DNA and RNA, and of proteins, and what are their distributions. Because that's the other thing, is that you need to be able to say this wasn't delivered by meteorites. This is evidence of life. In order to do that, you need to know what the distributions of these things in life are versus the distributions in meteorites. That's why meteorites are so valuable, is um, because they have we like there here is evidence of how chemistry would give us these things, um, but But in life, it's completely different. Like, for instance, proteins are made up of all left-handed amino acids. But meteorites have both left-handed and right-handed amino acids in more or less equal distributions, because chemistry doesn't care whether it's left or right-handed. It's going to make these things equally. But life cares a lot. Life needs things all to be one. It's called chirality. It needs to be all left-handed or all right-handed. So um, looking at those kind of signatures is going to be key to figuring out, okay, this is actually evidence of life and not just of some organics delivered by meteorites.
Oh, I see, I see. And I guess, I mean, if the organics were delivered by meteorites, does it really matter? I mean, if the original life was created by meteorites, but it lived on Mars, does it really matter?
Uh, I mean, it would be exciting because it would be evidence that this scenario that could have happened on the early Earth also could have happened on early Mars. But what you really want to find is some sort of smoking gun for life. You want something that's clear evidence that life was there or life is there. And there's ways to do that with the instrument, the Sherlock instrument. Um, but they have to have the right sample. They have to sample the right place where there is life, or where there once was life that's been protected somewhat from degradation, because there's strong ultraviolet light on Mars. There's galactic cosmic rays, so you want to choose your location wisely. And it would be awesome for a geologist, or a geochemist to go there and like find these niche environments and take a bunch of samples. But these rovers are really valuable at doing that without us having to send a human there.
Very true.
Yeah.
The last time we spoke, we didn't have enough time to speak about Venus.
Oh
And
yeah,
about the news that came out of there, and that was pretty big as well. I think it's been overshadowed by all the stuff on Mars,
yeah,
which is why I wanted to bring it up anyway, but, Venus is a big deal. There's, I think rumors of water or something. Do you wanna touch on that for a minute here?
yeah, for sure. So the big phosphine debate kind of was super topical for the last. I mean, I would say it's now gotten to a point where it's kind of like you say, like kind of trickled out of the news a little bit, but without a perfect resolution. But there was a period of time, I would say probably in October, November, December of last year, where it was in like there was a new paper coming out daily about like analyzing these observations in a different way. Continuing this debate on whether it was actually a signal or not. Scrutinizing the models. It was a and it got it got a little bit catty too. Like some people said some things that sent people you know off on yeah. So anyway, the gist is that uh, this detection came out of phosphine, which is a phosphorus atom attached to three hydrogen atoms, and it's not a particularly well known species, not really talked about a lot, but it is made by certain organisms, microorganisms on Earth, and it's not really produced any other way other than on Earth, at least other than by life. Um, so what they did is they found this. They took two different telescopes, James Clerk Maxwell Telescope and the ALMA Telescope, and they observed Venus's atmosphere, and they found the signal using both telescopes. And the James Clerk Maxwell Telescope observation looked okay, but it was kind of weak. And then the ALMA one, which is like 66 antennae, it's essentially working like a 15-kilometer size telescope, because it's got like all these different dishes at different distances. Gets this excellent. What I mean, I'm not an observer, but to me, the signal looked amazing. It was just so clear, so strong. And then they ran some models to try and figure out, okay, well, what kind of abundance is this? And they kind of settled on 20 parts per billion. And then they looked at the chemistry and they said, okay, well, there's actually no way that chemistry could make this amount of phosphine, and there's no way that the physics of the atmosphere, the mixing and stuff, could build it up either. So what if we put in an unknown source of phosphine at about 50 kilometers up in the atmosphere, and then rerun our models, oh, now we can get this signal. So now now this unknown source is kind of this evidence that, one of the things it could be is life. So that was really exciting. But then in the process of science, it's like now the scrutiny starts, and it seems like it was just piled on for the next 2 months onto this team. In some ways, in at least a couple ways, a little bit unfairly too, just in the language that they were using. But they essentially were scrutinizing the detection itself and the way that you process the data. And this is where it's really hard to explain. And I'm no observer, so I can't really do it justice. But essentially, you got to fit your data sample or your data that you get. You got to fit it to try and pull the signal out of the noise. And in doing so, you may be introducing a signal that wasn't there in the first place. But the team since then has come back, reanalyzed, and is doubling down that this is an actual signal, not a result of processing. So we don't know. More observations are needed, I suppose, because it's still very interesting what's going on, whether or not it's true. But
So
I
just to
guess
recap,
see.
then essentially what you're saying is that there's a signal of phosphine, not water. It's
Yeah,
phosphene.
phosphine. Yeah.
And phosphine is something that is usually created by life on Earth
Hmm.
that we know of. So we don't know what's actually creating this potential signals of phosphine on Venus.
Yeah, and there's no known chemistry which could make it. And
Whoa.
I emphasize known because actually we don't know enough about phosphine yet, which is uh, which is actually really exciting because it's. I even wrote a proposal actually for one of my postdoc applications to try and uncover all this unknown phosphine chemistry to rerun the models and see, okay, is it just unknown chemistry? But I mean, it's important research to do, but I don't know if that would have turned up if with any different results than the initial models.
Right. So, I mean, again, this is an area that I don't know a lot about. I mean, it seems to me like what you guys do is a little bit of physics, but it's also a lot of chemistry.
Hmm. Yeah, yeah. Isn't that weird? Actually, so I call myself an astrobiologist and astrophysicist, but probably the majority of my work is chemistry.
Right.
But that's just the nature of. I mean, astrobiology. We haven't found any life beyond Earth yet, so there's no life to analyze. So it's really more focused on chemistry and how to make life using getting from that transition of chemistry into biology and figuring that process out and looking for the kind of chemicals that life makes. So it is really more about chemistry.
Yeah, and I'm really curious again about this whole phosphine situation. So, do we just kind of keep analyzing it, keep observing it, and see if we keep noticing it? How come we never saw it before? Is another thing that I'm really curious about. Because let's touch on that one. Is it because our telescopes are just so much better now that this is the reason why we're spotting it now? Perhaps.
I think there's a few things. One thing is that you have to be looking for it. Um, so the signal will come at a very specific wavelength, and very specific telescopes can observe at that wavelength. So you have to, and this is the interesting thing actually is that they after this detection they went back to some old data from a orbiter that did some mass spectrometry, and they were like, oh, did we actually is this signal in here too? So sometimes you're just not looking for it, so you don't find it because you're not looking. But in other cases,
Hold up, I want to know. Did they find the signal in that?
I think they were able to put upper limits on the amount that was there, but they didn't have a like a
They weren't looking for it.
strong detection. Yeah,
Oh,
in
okay,
the
okay.
old data. Yeah. Um, so they what was I saying? So they
Oh, we just talked about the orbiter. That's and you just
yeah.
mentioned it kind of in passing, and I had
No,
to stop you there because I needed to know.
that is completely fair. Oh yeah. So why didn't they find it before? The other case is like you say is that these telescopes like ALMA just went into commission in like 2012, pretty much. um, and a lot of its first kind of targets to look at weren't Venus. It wasn't our next door neighbor because it could go so much further and see so much cool stuff. So all these telescope proposals have to go through, and then eventually the one that looks at Venus gets accepted, and then they look at Venus, and then they're like, what molecules can we look for? And if phosphene's one, then they're going to attempt to pull that signal out of the data. So I think the way it happened was that they using this James Clerk Maxwell telescope, they found the signal and they used that as kind of leverage in their proposal to use ALMA to try and find the same signal. So it's kind of the unfortunate process sometimes in observational science, which is key. It's important that there's these competitions for telescope time, but unfortunately, it could take years before you're actually able to observe the thing you want with the telescope you want.
It's gotta be frustrating to be that one or scientist or that team of scientists that's like, "Oh my god, we might have life on Venus."
Yeah,
And to have to wait,
yeah,
and to have to wait, and to have to wait, and meanwhile, all the attention is going on Perseverance right now, and
yeah, yeah,
they're like, "Yes, but Venus."
yeah,
So
exactly.
so I have to ask you a question about your field in general, which is, what are some common, disagreements within the field? Like, what are some things that you guys don't always agree on?
Yeah, there's a lot. Probably the biggest one in my direct field is the site of the emergence of life, and I think we maybe touched on this a little bit last time. Is this kind of warm little ponds versus hydrothermal vents?
Right.
So this is a very common debate that's still emerging, and we still talk about it at conferences. There's still people on both sides doing great research, and it's really good for our field to have this kind of conflicting hypothesis driving research, because as long as everyone's respectful, which in most cases is the case, um, we're both learning from each other a lot. One hypothesis kind of pulls ahead, and they're like, "Oh, well, we can do this," and then the other is like, "Oh, well, we can do this," and then eventually one of them is going to surpass the other in terms of evidence. There's going to be some kind of barrier that one can't overcome, and then the field will drive more research towards the winning hypothesis, and then I'm sure it'll then split into two in some way again.
Right.
They'll find a way to have contesting parts to it.
What's been your experience with Canadian research? I know that in the United States, there's SpaceX, there's NASA. We talked a little bit about the potential jobs in the United States, but now I'm really curious about the Canadian space research, Canadian research into past life, things
Mhm.
like that. Are there areas that you think need to be improved, perhaps?
The field in Canada is pretty small. Um, I'd say like we have what we call the Canadian Astrobiology Network, and there's probably about 2 dozen at the most professors and postdocs and students who do origins of life or astrobiology research. And sometimes we meet. There was the Canadian Canadian Space Exploration Workshop in 2016, where we all came together and wrote these reports for the Canadian Space Agency, trying to tell them, here would be the coolest science that Canada could do. Um, and with the budget that Canada has, we generally don't do missions on our own. We usually tag on to another science mission. So we'll put one instrument on a mission to a planet or a moon, rather than drive the whole thing. Just because we're too small, we don't have enough funding to do that all on our own. But it's important that we get together and say, okay, well, what do we all want to do? And we'll talk to the astrobiologists, we'll talk to the geologists, we'll talk to astronomers and all these different groups, and try and find the coolest targets. So one that came up in that meeting was a lot was Enceladus, Saturn's moon, which has geysers that kind of expel a bunch of stuff from the interior, and it's got a subsurface ocean. So this it's kind of giving us free access to the subsurface, and everyone agrees you want to go into the subsurface because that's where the pristine stuff is. That's where, if life exists, it'll be surviving. So if you have these geysers shooting its insides out into space, we could just take a space probe and fly through it and collect all that stuff and then analyze it and see, is there evidence of life here. At least that's what we want on the astrobiology side are interested in. And then the geologists will be like, okay, what rocks are here? And, what can we say about the tectonic processes and stuff like that?
That sounds I didn't know about Saturn's moon.
Hmm.
So it's got geysers and it's got an ocean?
Yeah, yeah, subsurface. So it's got, something like maybe 10 kilometers of ice. And then below that, it will have um, it will have a liquid water ocean, and then below that it actually has, and this is what's so interesting about Enceladus, because you may have heard about Europa, Jupiter's moon, which also
Yeah.
has a subsurface ocean. But the kind of distinguishing difference is we have evidence with Saturn's moon, Enceladus, that there is water rock interaction, a process known as serpentinization, which expels hydrogen gas. And they've measured this hydrogen gas coming from the kind of the cracks on the surface. So the water rock interaction is kind of critical for the hydrothermal vent hypothesis, because you need your vent to be in direct contact with the water. And there's no evidence at this stage for Europa having the same contact.
So could Canada feasibly afford to send their own probe to Saturn's moon?
Not on our own, um, but if there was a push, NASA, for example, if there was a push to go to Enceladus, say, Canada could put money into an instrument to, say, analyze organics from the geyser. Um, One thing, we kind of work within our areas of expertise, and there's a lot of great people who did, like, for OSIRIS REx, I believe the laser radar, which was basically crucial for the thing not crashing into the asteroid,
Mhm.
and knowing how close it was to the surface so that it could grab the sample, was developed by Canadian scientists. Um, so we have kind of a history of certain instruments that we do, and as a result, actually, Canada now gets some of the sample that's going to be returned from that asteroid. It's kind of like,
Oh.
you put in the money for the instrument, then we're going to give you some of the sample. So scientists in labs in Canada will be analyzing some of that.
Okay, so that would go to government labs, right?
It'll go to specific researchers who kind of kind of signed up on the uh, uh, on the team at the stage when they were developing all this, and they've kind of been key throughout the entire design process, and on everything from the get go. So I guess it's been long known which labs are going to get some sample. But yeah,
Wow, it's so I mean, it's amazing to me every time I speak to a few scientists, I mean, obviously for this podcast, but speaking with you, you're the only one I've spoken to really about space. So I'm always learning new things, especially about exoplanets and moons and life, the origins of life and all that stuff. And I'm like, I want to send robots out right now. I don't know how you guys. I honestly do not know how you guys keep being so patient.
yeah, I know. I agree. Like, one of the most exciting missions that I'm looking forward to is the Dragonfly, um, going to Titan,
Okay.
Saturn's moon, and that's not going to happen. So that just got awarded its kind of final round of funding, and I believe it's not going to be launching till 2040, 2040s. So you got,
Really, I thought it was sooner than that.
it may be like the late 2030s, but it's still quite a while. So you start to think like, oh man, like, where am I going to be in my career at that time? Like, is it too early to do kind of preliminary research for this? Should I focus on something like Mars, where there's going to be results coming out in the next decade? So yeah, it's really hard, but yeah, these are long. This is a long process, and these are long missions. I just hope that, like, maybe our astronaut program advances fast enough that humans may get to some of these places soon and do some of the science without the necessity for space probes. But maybe that's a little bit far away.
Do you think it's really that far away that we'll be going to Mars, for example?
Uh, I think the moon is going to totally happen this decade, 100%. And then with Mars, because there's so many different initiatives that are interested in going to the moon right now. There's so much money being thrown into that plan, and it's going really well. Actually, all the testing of the different spacecraft and different rockets. There's many companies working on that. Um, on the Mars front, it's kind of like, okay, well, if the moon phase goes well, then yeah, it could happen as well later in the decade, or maybe the following decade. And I always am the eternal optimist about this, because I love the idea of exploring, of human exploration of space. So if you ask me, I'm going to say yes, uh, but that's just also my personality. So
Now we have, I mean, obviously we've studied, we've gotten samples back from the moon. Did we? I mean, I haven't really read up on that because this happened before my time, obviously. But the samples that we got from the moon, was there any information in there in regards to the origins of life?
uh, no, I don't believe so. I mean, one of the coolest things from the lunar samples was that's actually been really relevant to my research is figuring out what the rate of meteorite bombardment was at the time of the origin of life. And this kind of tells you, like, okay, how many ponds on the surface are being seeded with meteorites. Well, you need to know the rate at which asteroids are hitting the Earth, and it was much higher at that stage because there was just a lot more. As the solar system was forming, there was a lot more debris everywhere, and then eventually, with all the forming of the planets, this debris kind of got swept up and either kind of collided with planets or the star, or kind of ejected out of the solar system. So we've been in this process of cleaning up our solar system for billions of years. Back then, it was just a mess. So asteroids were bombarding the surface at a rate kind of 100 million to 100 billion times what it is today. Today we hardly notice when a meteorite enters the atmosphere, but back then it would have been like shung 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 shung, and it's everywhere. So that's from the lunar samples. They measured the ages of the largest craters, the largest basins, and because large things impact less frequently, you can kind of tell um, at what rate different sizes of these things impacted at those dates in which. And the idea is that, like, the moon is kind of a pristine sample of the craters, because there's no tectonics, there's nothing removing these craters on the moon. So you're looking at a good historical image of what the bombardment was on the Earth. If the Earth didn't have tectonics or life or anything, those craters would still be there, and we could just look at ourselves. But lucky for us, we have this moon to look at.
It's funny because I'm originally from Sudbury, right? Which
Oh yeah,
is like the site of a massive crater, right? I mean,
yeah,
I think it's one of the reasons why it's so full of nickel.
yeah.
I don't know. I mean,
No,
I'm not a
that's it.
geologist, but I
Yeah,
think that's it, right?
yeah, that's it. Yeah,
Yeah,
yeah. The
yeah.
Sudbury crater is one of the coolest ones. It's so old too. I think it's something like 100, no, maybe 100 million years old, or it could be a billion even. It's so old that tectonics have stretched the crater into an ellipse. Um, because all craters are circles. They're all like symmetrical. Because it's essentially an explosion in the ground, and explosions are uniform. They don't care. They don't have a specific direction that they like to explode. It's just everywhere. So the fact that it's oval is evidence that it's been so long that tectonics have just kind of stretched out that crater.
I didn't know that. I'm actually making a note right now to tell my friends in Sudbury because I actually didn't know that about my hometown. That's really unique, and it is, it's if anybody's ever been to Sudbury, you'll know that it was a crater because it's all rock. I mean, it is literally all black rock.
Yeah.
It's this
Yeah.
amazing. I mean, they've planted a lot of trees in the past decade or so. I mean, it's a completely different landscape, but it
Mhm.
is very unique what the craters have done to the Earth's surface. Um,
Mhm.
Staying on Earth on space exploration. So you're excited about? I think they're building a base on the moon, right? I mean, I think that's what they're planning to do.
Yeah. Yeah. That's
Is an
the
actual base,
That's the plan. I know the Chinese space agency is pushing forward on the base module. They're doing like a lot of different lunar module designs right now. The thing that Canada is involved with, which is really exciting, is the Lunar Gateway space station, which will be orbiting the moon and is kind of like the gateway to deep space. So if you want to go to Mars, you first go to the Lunar Gateway, and then you ship out from there. So it's kind of like a shipping off point.
like a docking station.
Yeah, exactly. Like, all right, we're gonna go to deep space, so we got to go to our docking station first and fuel up or
Wow.
whatever. And yeah,
I mean, do you feel sometimes like you're essentially living all the sci-fi shows that you used to watch on TV?
yeah, for sure. But it just doesn't happen fast enough for my liking.
You're in what age range are you in?
I'm in my mid 30s.
You're mid-30s. Okay, so you're still young enough to see, like, potentially in the next 50 years what's gonna happen.
Yeah, yeah, I hope so. I certainly hope so. Hope to be involved.
Well, and that's the other thing is the fact that you have both feet inside this field. You can really not just observe from a kind of geeky point of view, but
Mhm.
also, be involved in it. So, what are you allowed to tell us what you'll be working on at Johns Hopkins?
Yeah, in general. So the cool thing about this position, and this was kind of really important to me, was that I take a position that has an experimental aspect to it, because a lot of my work has been theoretical research up until now, and I love theory, you know, but in my mind, you can't use theory to prove something exclusively. You need experimental data, and we use experimental data that we don't collect ourselves. But I would really love to do the experiments, collect the evidence that I could then use in um, unison with theory to really make some progress on some origins of life hypotheses. So I'm going to be doing experiments, which is not brand new to me, but definitely a new exciting endeavor, and um, it's going to keep me super passionate and super driven, which is why I really needed this. Is um, I'm the kind of person that I really love learning and doing new things. And if I was doing just theory, for instance, which was a couple other offers that I got, I probably wouldn't be as stoked as this case, where I now get to breach into this new experimental territory, do different atmospheric experiments, using actual ultraviolet light in a chamber with different gases to try and make uh, biomolecule precursors like hydrogen cyanide, like we were talking about, and then raining these down into little like ponds, experimental ponds, so that I can try and make more complex biomolecules that way. So it's really taking the theory I've been working on forever and then doing experiments.
That sounds so cool. I wish I could be a fly on the wall, to be honest with you. Like, when you're doing these experiments, are you gonna be able, do you think, to share videos and photos while you're doing these experiments? Is that something that John Hopkins, for example, is big on in terms of, SciComms, science communication?
I think that that's more to do with the personal scientist, because there's no rule against sharing your research journey through social media or whatever. And I'm definitely someone who likes to do that, who likes to do science communication and share what I'm going through. At some aspect, there's only so much you want to share because you want to save your exciting discoveries and give yourself time to analyze your own data before sharing it. But certainly pictures of what you're doing, like that's super safe and super super fun to do. Like if you have a picture of your chamber, or you show yourself kind of going through the process of running a gel, um, or analyzing your data. So yeah, I'll definitely do some of that for sure, and I don't see anyone having issues with that.
Please do. I really want you to, share a picture of that, at least a couple of pictures of the chambers. I'm really curious to see what that looks like.
Yeah, yeah, for sure.
Awesome. Well, listen, Ben, it's been a pleasure having you again on the show. We definitely finally talked about Venus, which is something I really, really wanted to talk about because it's. I'm definitely, I think, going to set up like a news alert or something for any news that's coming out of Venus. And
Yeah, that's a good
can you
idea.
tell people? Yeah, definitely. Can you tell people how they can follow you on Twitter?
Yeah, my Twitter handle is astrobio_Ben.
Great.
So you can check me out there, and that's probably where I do the most updating of kind of the science I'm doing or the cool science of other people that I want to amplify, what's going on in my life, and then also my website, which is www.benkdpierce.com, which is spelled Pearce.
I was just about to spell it for you. Anyway, thanks again for coming, and good luck at Johns Hopkins.
Thanks so much, Julie.